In this video, we're going to introduce the topic of chemical equilibrium. And actually, this video is going to be an extension of what we had looked at at the end of chapter 13, where we had started to kind of look at this concept of fast equilibria when we were doing mechanisms. So in this case, when we talk about equilibrium, we're going to be kind of dissecting that concept of equilibrium and looking at how we can do different things with it, different calculations, and making predictions about the direction a reaction might take. So one example that I like to point out, just to kind of get started, is a biological example. And this is something that the biology majors, and just everyone in general, because everyone relies on this equilibrium to breathe. This is kind of an important one, and it's a good example of a lot of the different principles that we're going to be talking about in equilibrium. And that is the interaction between oxygen gas, which is the gas that we need to breathe in and for respiration, and the hemoglobin in our bloodstream. So the hemoglobin basically is an iron atom that's locked into what they call a heme. It's basically just a chelating structure inside of the hemoglobin protein. And when these come together, they form a complex of oxygen-iron heme. So what we see happens is we basically see this principle of equilibrium because in the lungs, where oxygen is rich, the oxygen drives the forward reaction, and we form the complex of O2 iron heme. That is transported as a complex through the bloodstream, and then when it gets to the cells, where oxygen is deficient and the cells need the oxygen, it goes in the reverse direction, and the oxygen comes off and is able to be metabolized by the cells in respiration. So this equilibrium of iron, heme, and oxygen is really fundamental to our survival as living living organisms. And so what we're going to do is we're actually going to take a look at a slightly different example. And the example that we're going to look at is this example of 2HI gas breaking up and decomposing into H2 gas and I2 gas. And this is just a simple example. There are so many examples of things with equilibrium, but we're just going to start here because this is a nice simple example with nice simple molecules, and we can track things. So what we're going to do is we're going to take some HI, and we're going to just do, in this case, we're going to do the number of moles. So we're going to plot moles on the y-axis, but it could also be concentration, and we're going to plot time. And what we're going to do is we're going to take some HI and we're going to put it into a rigid container with a fixed volume. And then we're going to let that container come to equilibrium at a given temperature. Now, the reason why I can say that moles and concentration are related here is because the number of moles, concentration is the number of moles divided by the volume. And since the volume is fixed for all of the different species that are going to be formed, HI, H2, and I2, in essence, they're all going to have the same bottom part, so we can kind of think of that becomes a constant, the volume, and then we can really just kind of focus on the number of moles. We're actually going to see this as kind of a defining principle for equilibrium as we go along, that the container is a rigid container with this, where all species in the equilibrium are within the same volume. And so what we're going to do is we're going to start with some initial conditions. So our initial conditions. And what we're going to do is we're basically going to set this thing off with the number of moles of HI, or our concentration of HI. And remember, we're just going to kind of ignore the volume because it's going to be the same for everything. So I am going to note that this is concentration, but we're just going to use moles for simplicity. So we're going to start initially with 0.100 moles of HI, and we're not going to have any H2 or I2 initial. We're just going to start this thing with just some HI, and we're going to let it decompose. So we're going to start this with 0 moles of H2 and 0 moles of I2. And so if we put if we kind of put some units on here, that's not O2, that should just be 0 moles. If we put some units on here, we can get some scale for the reaction. So our starting point for the HI is going to be up here at the 0.1 mole marker, and then we're going to also put on here 0.5 and 0.25 just as other markers to keep us sort of in place. Now, if you think about this, we can write the rate of the forward. So the rate of the forward is going to equal the K of the forward, the rate constant for the forward, times the concentration of HI. And because this is an elementary reaction and we're writing it in the forward direction, we know that since this is an elementary reaction, we can put that it's going to be squared. So we know that two HIs have to come together in the forward direction. And for the reverse, we can write that the rate of the reverse is equal to K of the reverse times the concentration of H2 times the concentration of I2. And again, I can write those with using the stoichiometry because these are elementary reaction steps in this. This is not describing the entire reaction. This is describing the elementary reaction of the forward and the elementary reaction of the reverse. And we're going to see this sort of principle throughout. So now when we think about this, and we're going to use these throughout the entire analysis of this system. So when we start, we have some HI, but we have no H2 or I2. So what's going to happen is basically the rate of the forward is going to be much, much greater than the rate of the reverse at the very beginning, right? Because we have a lot of HI around, relatively speaking, but we have almost no H2 or I2. So in essence, this thing is going to start to go forward, and we're going to start to lose HI. That's going to start to go away, and we're going to start to bring in some H2 and some I2. That's how it's going to start. But now, as time goes on, what's going to start to happen is, sort of as the reaction proceeds, so we'll put progress here. So as the reaction progresses, what's going to happen is the concentration of HI is going to go down from its initial, and the concentration of H2 and the concentration of I2 are going to grow in. And so what's going to start to happen is that the rate of the forward is going to start to go down, and the rate of the reverse is going to start to go up. And what we're going to see is we're going to start to see that this is going to start to slow down, and then this is going to start to come in. And then what's going to happen is that after a given point in time, these traces are going to come to a halt at a specific position. And this is what we're going to call equilibrium. So then at equilibrium, we're going to be able to talk about and predict the concentrations of things. But for now, the way to think about this is as the H2 and the I2 start to build in, the rate of the forward starts to come down a little bit because we've used up some of our HI, and the rate of the reverse starts to come in a little bit. And eventually they're going to get to a point where the rate of the reverse and the rate of the forward and the rate of the reverse begin to match each other. The two rates are going to start to sort of come to a balance, and at that balance is when we're going to have equilibrium. So at equilibrium, the rate of the forward is going to equal the rate of the reverse. And this is really important. That's the most important thing that we come to know about equilibrium. So when we get to this point where the rates start to tail off here, this is where we have equilibrium. So our concentration gets to a point where the net concentration stops changing, and then that's it. That's when we get to equilibrium. So let's talk a little bit about what's going on at equilibrium. So we said already at equilibrium the rate of the forward equals the rate of the reverse. And so if that's true, it's interesting that when we get to that point, it looks like we have two flat lines. So in essence, if this were the case, what you would think is that nothing is happening anymore. You'd have this sense that if the lines are flat and the concentration is not changing with respect to time, that might be an indication to you that the reaction is stopped or that the rate has gone to zero. However, that is not true. What's actually happening at equilibrium is that it's a dynamic process. And by dynamic, what that means is that products are being produced, and then they're going also in the back direction, and so reactants are also being produced. And what's special about this is when you reach equilibrium, since the rate of the forward and the rate of the reverse are the same, whenever you make some products, those products go back and make some reactants. So the net effect of this is that the concentration change kind of stops, because now, since the rates are the same, whenever you make some of the product, the product goes immediately back and makes some of the reactants. So these processes are still taking place and they're competing with each other. And the reaction is still dynamic. It's just that the net concentration doesn't change. So there's no net change in concentration. And another thing is at at equilibrium, the reaction contains a mixture of products and reactants. And you can see that here. There are some products hanging out. So this trace up here, this trace up here is HI, and this trace down here is I2 or H2. And we're going to talk a little bit in a second about what's going on with the stoichiometry here. We're going to kind of look at that in sort of the next phase of this video. And then we're going to actually go into that in a little bit more detail, but we're going to talk about how I came up with these numbers in a second. So that's the idea with equilibrium. The rate of the forward is equal to the rate of the reverse. It's a dynamic process where products are being produced and reactants are also being produced. So the reaction is going in both directions. And because the rate of those directions both directions are the same, you don't have anything winning out anymore. So there's no more net production of anything. The concentrations stay the same, although things are still going back and forth. And in order to have an equilibrium, you really need to have a mixture of the reactants and the products together, because you need to have appreciable concentrations of both in order to have the forward and reverse rate be on par with each other. So that's kind of the important thing. Now, I do want to mention one thing about this. So at equilibrium, I want to point out some things about those concentrations, because those concentrations are not were not chosen randomly. If you look at the stoichiometry, we have 2HI goes to H2 plus I2. And so we see that there's a relationship. For every 2 moles of HI we consume, this is going to equal 1 mole of H2 that we produce, and that's also going to equal 1 mole of I2 that we produce. So if you look at the numbers, we went from, our HI went from 0.1 to 0.05 moles. And so in essence, we've consumed a total of 0.05 moles of the HI. So it makes sense that if we consumed 0.05 moles of the HI, then by stoichiometry, the amount that we're going to produce is going to be half of that, because for every 2 moles of HI, we have 1 mole of I2 or H2. So this is going to give us 0.025 moles of H2 produced. So if you look at this graph, and I made a little mistake on my graph axis, which I'm going to fix right now, so that you guys don't yell at me. This should have been 0.05, and this should have been 0.025. I just made a little mistake there. You'll notice that we had that I didn't just make up numbers. This is actually what happens. This gets to 0.05, so we used up half of it, and we produce, by stoichiometry, 0.025 moles of the H2 or I2, which is what we would predict from stoichiometry. So that's something I want to mention, and that's actually going to be the topic of the next video, which is how can we predict, based on the stoichiometry, what the equilibrium concentrations of a mixture should be.